Hello and welcome to the first experiment under control engineering. And in this experiment, we are going to be looking at DC motor control using negative feedback. Before we move straight into the experiment, let's try to establish some theories about DC motor control. From our theory classes, we know that we have quite a lot of different types of DC motors. So we have separately excited motors, there are series motors, there are shunt motors, and also there are compound motors. So to see how we can control the speed of a DC motor, let's take an overview of how a DC motor works. So I'm going to be making an illustration here. So if we assume that here we have the core of a DC motor, which is the stator of this DC motor. So we have our magnets. So here we have our stator, which is the stationary part of the DC motor. So this is the south pole, and then we have the north pole. So inside we have the armature suspend, which is just a combination of coils. And then we have our armature. So yeah, current is being passed through to the armature through a battery or any DC source. So this can be the positive, and also we have the negative terminal here. So as current is applied through the terminals, the armature rotates, and the armature is simply the combination of individual electrical coils connected together. So at first instance, one of the armatures rotates as current is passed. When this particular armature goes out of scope, current is passed from the motor terminals to the next set of armature via the carbon brushes located around the commutator. So as all of the process takes place, magnetic field is being produced, and the energy produced causes the armature to rotate. So basically, if we pass current through the terminals of a DC motor, we're going to have one of the armatures to rotate, and through the commutator, when the armature goes out of scope, it's going to be passed through to the second armature, then lastly to the third armature, depending on the number of coils inside the armature. So from this scenario, we can see that the rotational speed of a DC motor majorly depends upon the interaction between two magnetic fields. The first one is the set of magnetic fields that is generated by the stator permanent magnet. So we have that some magnetic field have been generated by the stator permanent magnet, and also the other by the armature's rotating electromagnet. Two magnetic fields have been generated, one from the stator and the other one from the armature. So if we can control this interaction, we can control the speed of the DC motor. So if you're able to control either the stator magnetic field or the armature magnetic field, so you'll be able to control the speed of this DC motor. And one very easy way to control the speed of a DC motor is to regulate the amount of voltage across the terminals. So we can achieve this by using a pulse width modulation. So one of the ways that we can regulate the amount of voltage we have at the terminals of our DC motor is to use a pulse width modulation. And if this is arranged in one way, we are going to have the motor to be controlled using negative feedback. So how can we use a pulse width modulation to control the speed of a DC motor? This is what we are going to be looking at majorly in this experiment. Now let's try to establish some theories around pulse width modulation. After we have already established the fact that pulse width modulation can be used to control the speed of a DC motor. So let's now explain the concept of DC motor before we start doing the circuit design. Pulse width modulation, or is often referred to as PWM, is a digital technology that generates analog signals by using a digital source. A pulse width modulation PWM is basically a square wave that is switched between on and off states. And what determines the behavior of a PWM are simply the duty cycle and the frequency. So if you say it become a pulse width modulation might typically look like this. A wave that alternates between the off state and the on state. So if you're able to generate this kind of signal with our electronics and feed the signal to the input of a DC motor, then we can use it to control the speed of a DC motor. And as I mentioned, there are two things that basically determine the behavior of a pulse width modulation. The first one is the duty cycle. And this refers to the ratio of the time that the signal is in high state over the total time it takes to complete one cycle. So it's commonly expressed as percentage. So let me show some example of duty cycle. If the total number of time the waves takes to be in on state is the same time total number of time it takes to be in off state, this is simply a 50% duty cycle. Meaning that it takes 50% of the time to be on and also 50% of the time to be off. So we also have 75%. If it takes 75% of the time to be on and the rest 25% of the time to be off. So this is going to be 75% duty cycle. So that's basically how duty cycle can be read. The same thing, we can have 25% duty cycle. It takes 25% to be on and 75% of time to be off. So this is 25% duty cycle. So if you have 0% duty cycle, it means the signal is off the whole time. And if we have 100% duty cycle, it means the signal is on the whole time. So we are going to be using our electronics to generate this type of signal, and we are going to feed the signal to the input of our DC motor, and with that we're able to control the speed of a DC motor. The other thing that we have to take note of while generating a pulse width modulation is the frequency. And the frequency is simply the speed at which the PWM completes one cycle. Or we can say that it's the number of periodic changes in a unit time. So taking note of the frequency and the duty cycle, we can make our calculations to generate a PWM, and we can serve the PWM to the input of our DC motor. So how do we generate a PWM in electronics? So we are going to be using a 555 timer connected in astable mode. Or they also call this the oscillator mode. So with this principle, we can generate a pulse width modulation and pass it to the input of our DC motor. So now, after understanding the concept of DC motor and also understanding the concept of PWM, with these two theories, we can use it to design our circuit to control the speed of a DC motor using negative feedback. Now to the circuit design. Naturally, if you have a battery here and connect this to a DC motor, current is going to flow to DC motor and this will start to rotate. But in this case, we want to control the speed of this rotation. So how do we do this? So we are going to be using a DC motor, and we are going to be using a 555 timer to control the speed of the DC motor. We are going to be having a 555 timer as a major controller of the DC motor. The 555 timer has a supply voltage of 4.5 volts to 16 volts, and the output current is usually approximately 200 milliamps. And we know that motors are current driven devices, so in case of having big motors, we might need larger current, but our 555 timer can't produce up to that amount of current. Then we need to drive it using a MOSFET. Take note of this. So first we are using a 555 timer, second we are going to use a MOSFET to drive the motor. So the output of our 555 timer is going to control the MOSFET, and the MOSFET is going to be controlling the DC motor. So, and in this case we are going to be using a MOSFET which is IRF, an N-channel MOSFET, IRF-Z44N. So it has a continuous drain current of 49 amps. It has a drain to source resistance of 0.032 ohms, and that's a drain to source breakdown voltage of 55 volts. So take note, we are going to be using a 55 timer and also an N-channel MOSFET of IRF Z44N. So let me start drawing out the circuit. But first, I will clear this. So here we have our battery source. You might have studied how, it might take time to study how MOSFET work, but I'll just be giving a quick overview of how a MOSFET work here. So here I have my MOSFET, which is IRF Z44N. So we have the drain, the gain, the drain, and the source. So these are 3 pins, and then I have my DC motor. So from here, one leg of this voltage supply is going to come to the DC motor, and from the MOSFET, we are going to have one leg, which is this drain, going to the ground. And we are going to have the drain of the MOSFET going to the other terminal of the DC motor. So here is going to be an input from the pulse width modulation circuit. So if you can build a circuit here, that will give an input of pulse width modulation, and if you can pass the input here, we're able to control the speed of our DC motor. And basically what we're going to be doing here is to build a pulse width modulation circuit using 555 timer, and we're going to be using 555 timer connection in a stable mode. So now let's design the circuit properly. So as I mentioned, we have our DC motor here, and through our MOSFET, we're going to have a MOSFET as I described, IRF Z44N. So I'm going to design the circuit in such a way that we're going to be seeing the working principle of the circuit. So I have our MOSFET at this end. So this is the symbol for MOSFET. So here we have the drain, we have the source, and we have the gain, the gate. So from the drain, it goes to the other terminal of the DC motor, and from the source, it goes to the ground. So everything you'll be doing inside this circuit is designing a pulse width modulation circuit, which is simply connecting a 555 timer in a stable mode. So but before we move into that, motors, they are like inductors. So therefore, if you are powering our motor from a 12 volt battery, so in case this switch is disconnected, there might be some kind of feedback from the motor that might want to spoil our MOSFET. Therefore, we are going to put a flywheel diode at this end. Usually to prevent feedback from this circuit. And here I'm going to be using a diode D1, and this one D1 is simply 1N4007. It's a diode of this number 1N4007. So let's assume we have our 555 timer here. So it has 8 pins. So 1, 2, 3, 4, 5, 6, 7, and 8. So the pin 8 is the VCC, which is simply the input to the 555 timer. So from 12 volts, it goes to the pin 8 of 555 timer, and pin 1 is the ground. So pin 1 goes to the ground. So that's the first thing we have to take note of. So as I mentioned, we are connecting our 555 timer in a stable mode. You can read more about this. This experiment is not about connecting 555 timer in a stable mode, but what we're going to be doing is connecting 555 timer in a stable mode. So you can read more about connecting 555 timer in a stable mode to understand this circuit better. So one, we are going to be having the way 555 timer works. It works based on timing capacitor and a timing resistor. If you are connecting in a monostable, we only have one timing capacitor and one timing resistor. But if you are connecting in A stable, which is the oscillator mode, we have two timing resistors and one timing 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 capacitor. So these are going to connected in some certain ways. First, we are going to be having a charge and discharge part for our 555 timer. So I'm going to be explaining some of the functions of this component. So the first time we set up our 555 timer, pin 3 is the output of the 555 timer. Pin 3 is always the output of the 555 timer. And when the output of the 555 timer is I, which is pin 3 is I, the discharge pin is the pin 7 is open, forcing the current to pass through the resistor R1. This is our R1 resistor and also resistor and capacitor C1. So whenever this is open, let me connect this together. So pin 7 will be connected to R1. Again, pin 7 is the discharge pin, and with the output I, pin 7 is open. It's now force current through R2 and C1. So we have a potentiometer here to vary the current passing through C1. So here we're going to have R2 and R3. So whenever we are changing the value of our potentiometer, it's going to be changing the value of R2. So our R2 comes from the potentiometer. So with output I, the discharge pin, which is pin 7, is open, and this forces current through R2 and C1. So this causes the capacitor to charge at a rate that depends on R1 and R2. Pin 6 and pin 2 are connected together. And as the capacitor charges, the voltage at pin 2 and pin 6 increases. Because here we are going to have the output of this point goes to pin 2. So we have in between R1, R2 and C1, the output there goes to pin 2. So pin 2 is our trigger and pin 2 is connected to pin 6. So as the capacitor charges, the voltage at pin 2 and pin 6 increases. And those are the major two important connections in our stable mode connection for timer. So when the voltage at pin 6, which is the threshold pin, which is 2/3 of the supply voltage, the threshold circuitry within the 555 timer causes the output of the pin 3 to go low. When the output at pin 3 goes low, the discharge pin, which is pin 7, is connected to ground within the 555 timer. So this allows C1, which is our timing capacitor, to discharge, and this discharge occurs through R2, so that the value of R2 as well as the value of the capacitor determines the rate at which the capacitor discharges. So at this end, we're going to have the charging parts, and at this end, we have the discharging part. So here we have two diodes. So through this diode, our capacitor charges, and through this diode, our capacitor discharges. So that's the major point why we have two diodes there. And as the capacitor discharges, the voltage at pin 2 and pin 6 decreases. So whenever this capacitor is discharging, after charging it up, whenever our pin 3 goes low, the capacitor starts discharging. And once it starts discharging, the voltage at pin 2 and pin 6, because they are connected together, it starts going low. And when the voltage of pin 2 drops to 1/3 of the supply voltage, the trigger circuitry inside the 555 timer causes the output at pin 3 to go high. So whenever this begins to drop up to 2/3, the voltage at pin 2 begins to drop up to 2/3. So the trigger circuit inside this 555 timer causes our pin 3 to go high. So when the output is high, the discharge pin again opens and the charging cycle starts again. So from our pin 3, we're going to have the input through a resistor to the gate of our MOSFET, and the output here is going to be in form of a pulse width modulation. It's going to be in form of oscillation. It can be a square wave depending on some calculations. So after finishing the major connection in our circuit, let's do the other part of the connections. Our pin 4 is going to VCC. Let me just write this here, which is our 12 volt is going to be positive part, and pin 5 through a capacitor is going to the ground. And with this, we have the full setup. So with this, if you can replicate this circuit on a circuit board, if you can control our potentiometer through this, you're able to control the speed of this DC motor. And there's some basic calculations that we need to take note of if you want to design a circuit as this. As you know that the major determinant of the speed of this motor is the wave that comes from the output of our 555 timer, which is the output from pin 3. And you can control what comes out using the charging and the discharging part through this potentiometer. So therefore, if you can calculate the time for our wave to be on and also the time for it to be low, you can control the values of both R1, R2 and C1 to control the speed of the DC motor. And how do we control the charge time? So one of the calculations we have to take note is the charge time. And this is calculated as T on. It's simply 0.693 multiplied by R1 plus R2 multiplied by C1. So assuming for this circuit we are using R1 to be 1 kilo ohm, R2 is 50 kilo ohm, R3 is 50 kilo ohm. What this means that because we are using a potentiometer, we are using an 100k potentiometer. So on a potentiometer has a wiper. As we are increasing it, the resistance keeps increasing. As we are decreasing it, the resistance keeps decreasing. So in case of we having R1 to be 1k, R2 to be 50k, and also R3 to be 50k. So here we have our, let me explain this again. On our potentiometer, we have two parts for resistance. So as we're increasing it, it keeps decreasing, it keeps dividing the resistor. So we can vary the resistor in between R2 and R3. For example, if this potentiometer is 100k, we can start splitting it by 50k, 50k, or 70k, 30k, depending on how we move the wiper. So if you're able to put the potentiometer in the middle and we have R2 to be 50k and also the R3 to be 50k, and we use a value of 10 picofarad for our C1, we can calculate our on time as T on is equal to 0.693 multiplied by 50k R1, which is 1k plus 50k multiplied by 10 picofarad. And this is simply 0.00 1. So here we are going to have our T on to be 0.35 milliseconds. Same thing, T off if our capacitor charges through R1, R2 and R3, as because we have this as the charging part, it's going to discharge through only R3 without having to go to R1 and C1. So our capacitor discharges, it charges through R1, R2 and C1, but it discharges only through R3. So we're going to have our T off to be equal to 0.693 multiplied by R3 times C1, and this equals 0.693 multiplied by R3, which is 50k or 50,000 ohm, multiplied by 0.00, we have 8 zeros, So this is 10 picofarad, and then we have this to be equal to 0.34 milliseconds. Another thing we have to take note is the total time that our cycle uses, which is simply the cycle time. So the cycle time is simply the T on plus T off. In this case, we have 0.34 plus 0.35, and this is 0.69 milliseconds. And lastly, one very important thing we have to take note of is the frequency. So the frequency is 1 divided by the cycle time. And in this case, we have 1 divided by 0.69 milliseconds, and here we have 1428 kilohertz. So if you increase the capacitor, the frequency affects how the timing cycle is. So, and for our DC motor, we need a very high frequency to control it. So whenever you are increasing any of this parameter, you should make sure that you have a very high frequency here, so we can easily control our DC motor. So this is simply how we can control the speed of a DC motor using negative feedback. These are circuits, and these are the necessary calculations. So now I'm going to be simulating this circuit using the software that we introduced in the last class, which is Proteus, and also I'm going to be using the real circuits, which is all the real components, to design this so that we can see how it behaves in real life. Now we are going to be simulating the circuit we just designed using the software that was introduced in the previous video. So make sure your selection is in component mode and click on P. So as you can see, we have the circuit design displayed on the screen. So the first thing I'm going to select from here is the DC motor. And if you don't know how to use the software, you can check the previous video again on how to use Proteus, or you can check the materials that was shared online on how to use Proteus. So I'm going to select simple DC motor model and click OK. So once I drop this, I have this in my environment. Also, I'm going to select a battery, which is going to be the power source for the motor and the whole system. A battery multi-cell. So I'm going to pick this and also drop it here. So I'm going to be working through this from one component to another, as you can see in the circuit design. So from here, I have the positive terminal. Let me zoom this a little bit. Okay, I have the positive terminal of the battery. Go to one of the terminals of the DC motor, and I'm going to have a MOSFET, which is IRFZ44N, that we are using in this tutorial, and connect it to this point. So simply search for IRFZ44N. And drop it here. So I'm going to carry out all the circuit arrangements now, and as we have seen in the previous explanation, the calculation and both the design for the circuit. So I'm going to be picking my fly wheel diode, which is 1N4001. So to go from one of the terminals of the DC motor to the drain of the MOSFET. So here I'm going to have all the pulse width modulation circuits at this point. So and I'm going to be following the circuit design that was carried out in the explanation. So what I'm going to need first is the 555 timer. So I'm going to drop this at the center of the circuit. So there's going to be, as you can see, there's going to be a resistor in between the pin 3, which is the output of the 5F timer and the gate of the MOSFET. So I'll just pick a 1k ohm. So you can type 1k here and select resistor to select resistor, and I'm going to pick a 1k 3 watts resistor, and I'm going to drop it at this point. So connect these terminals together, and also this will go to pin 3. Pin 4 will be connected to pin 8, and the both of them will be connected to the positive terminal of our battery. Pin 1 will be connected to ground, and I'm going to have my charge and discharge circuit. This is going to make use of a 1k resistor. This is what I have here. You can rotate it anti-clockwise. And again, I'm going to have the charge and discharge diode, as I mentioned in this theory, which have diode 1N4148. It has been selected. This is facing up. Also, I'm going to be selecting my potentiometer. You can search for port active. Select port active, click on OK, and you can drop it in the circuit. So I'm going to rotate this clockwise so that it can be better arranged on the board. So all the circuit is exactly according to the circuit that was designed during the theory class. So I have this connected. I'm going to connect now a 100 nanofarad as a timing capacitor. I can rotate it anti-clockwise. Connect this and also this. Pin 6 is connected to pin 2, and both of them are connected in between the resistor, which is the potentiometer, and the timing capacitor. Pin 5 is connected through and 0.01 microfarad. So I've just selected the same capacitor and change the name. So if you double click on the capacitor, you can change the value here. So just type 0.1 UF and click OK. So this is 0.1 UF, and again I'm going to rotate it anti-clockwise, and this goes to pin 5 and then to ground. Pin 7 is connected to this point. And lastly, we are going to need a ground in our circuit. So I can come to terminals mode, click on terminals mode, and select ground. You can bring our ground there. This is our negative terminal, and here we have the ground. So with this is exactly according to the circuit that was designed during the theory class. And as I mentioned, to simulate this, you can just click on the play button. But before that, I'm going to change this battery to a 9-volt battery. To a 12-volt battery, sorry. So once everything is done, you can just click on play to simulate this circuit. So as you can see, we have here that the DC motor is rotating. So to change the speed of this motor, I simply need to change the position of my potentiometer. If we move this towards 100, we can see the speed gets decreasing, and if I move it towards 6 and towards 0, the speed is now increasing. Again, let me move this towards 100. You can see the speed has reduced, and again, if I move it towards 0, the speed has increased. So this is the circuit design of how we can control the speed of a DC motor using pulse width modulation, which is negative feedback. Now I'm going to be building the actual circuit, and I'll be showing us how it looks like in real life. And and here I have the actual circuits that I've implemented on a breadboard. As you can see, this is my DC motor. Now it's at the lowest speed. It's moving very small. Here I have my MOSFET, which is IRF Z44N. This is my 555 timer for controlling the speed, and this is my potentiometer for varying the pulse width modulation frequency. So if I start to increase this, the speed of rotation is going to start increasing. And now it's at the maximum speed. So you can see that with this we can control the speed of this DC motor. So again, I can choose to reduce the speed. It's what you have here, and if I keep increasing gradually, the speed starts increasing. And this is the maximum. So that's it for this experiment. DC control the speed of a So that's it for this experiment. DC motor control using negative feedback. So the major concept of negative feedback there is, as explained, from the MOSFET. The source of the MOSFET is being fed to the negative terminal of our voltage source, and we use a pulse width modulation coming from a 555 timer to control the speed of the DC motor.